In this video, we shall discuss about the concept of limit for a function of two real variables. Before we start talking about that, let us quickly recollect the definition of limit of a function of one real variable. Limit x tends to a if x equals to L means for every epsilon greater than 0, a positive number epsilon, there exists a positive number delta, such that mod of fx minus L less than epsilon whenever mod of x minus a less than delta. So this is the formal definition of limit of a function of one real variable. Limit x tends to a if x is equal to L means for every epsilon, this symbol stands for all. So for all or for every epsilon greater than 0, this symbol stands for there exists a positive number delta such that mod of fx minus L less than epsilon whenever mod of x minus a less than delta. So this is what we mean by this thing, limit x tends to a fx is equal to L. Let us try to understand geometrically what this definition means. Let us consider a curve y equal to fx. Let us consider a function y equal to fx. It will geometrically be a curve like this. Let this be my y equal to fx. Let this point is x equal to a, and let this is my L, y equal to L or fx equal to L. So let this is my L. Now let us try to understand what this definition geometrically means. Firstly, this particular expression mod of x minus a less than delta. So if I investigate this expression, what do we get? Mod of x minus a less than delta. That implies a minus delta less than x less than a plus delta, which implies x lies in the open interval a minus delta a plus delta. Okay, so let us consider this is my interval of length 2 delta. That means let us consider this is my a minus delta, this is my a plus delta. Delta is a positive number. And similarly, this expression mod of fx minus L less than epsilon, if we similarly investigate this expression mod of fx minus L less than epsilon, what do we get? This will imply L minus epsilon less than fx less than L plus epsilon, which implies fx belong to the open interval L minus epsilon, L plus epsilon. Okay, so this is what this condition implies. So if we plot it again, say this interval, this is an interval of length 2 epsilon. Say this is my L plus epsilon, this is my L minus epsilon. So what this definition tells, the definition tells that whenever x, that means the variable points, lies in this interval, this open interval a minus delta a plus delta, the value of the function fx or the corresponding y value will lie in the interval L minus epsilon, L plus epsilon. Now, clearly, if you make delta smaller and smaller, delta very, very small, if you make delta very, very small, then clearly your interval a minus delta a plus delta will become very, very small. And if x lies in that interval, so we can say x and a are very, very close to each other. And since this delta and epsilon means if delta becomes very, very small, epsilon will also become very, very small. That is the requirement. That is what has to happen for the existence of limit. If when delta becomes very, very small, again if epsilon becomes very, very small, very, very small, then we can say that the functional value y and L are also becoming very, very close. So if we summarize the thing, this mathematical definition, whatever is written in terms of epsilon and delta, this means that whenever x becomes very close to a, fx becomes very close to L. If that happens, then we say that limit x tends to a, fx is equal to L. So I'm again repeating, whenever x becomes very close to a, if we see that fx becomes very, very close to a, then we say that if fx becomes very, very close to L, then we say that limit x tending to a, fx is equal to L. So the requirement is this. Now remember a few points to note, a particular point to note. Since a lies in the real line, x can approach towards a variable point ax can approach towards a only from two directions, either from the right hand side, either from the right hand side or from the left hand side. The variable point can approach towards a from two directions, either from the left side or from the right side. You can visualize the situation as a is placed on a rope and you have to reach to a by walking on that rope. So you can visualize the scenario as walking on a rope, because your all these values x, the variable point x as well as the point a, are lying on the real line. So you can imagine that you are trying to reach to a by walking on a rope like this. So you have only two options: either you reach from the left side or you reach from the right side. Consequently, when x approaches towards a from the right side, that is taking values which are higher than a, the value towards which fx or y moves means if the movement is something like this, if the movement is something like this means when when your x lies from the right side, that is by taking values which are higher than a, then the corresponding value of y on the curve will move like this, maybe this value, this value, this value, it will move in this way. So accordingly, in this interval, the movement will be, the y value will move on this line like this, like this. So it will move in this way. Now the value towards which fx or y moves in this way, if the movement of x takes place, then wherever the value of fx moves is known as the right hand limit and written as limit x tending to a plus. This plus indicates that x is taking values which are higher than a, fx, limit x tends to a plus fx. So it indicates that x is moving from the right side. Analogously, one can define the same the similar kind of scenario if the variable point approaches from the left side of a, that is taking values which are lesser than a, maybe something like this. It is taking, x is taking values which are lesser than a. As a result, the corresponding value of y on the curve is moving, means in curve the movement is like this, in this curve the movement is like this, and the corresponding value of y or L in the y axis moves like this. So if the scenario is this, if the scenario is this, and this is your corresponding value of, this is your corresponding value of a. So if the scenario is whenever your x takes values which are lesser than a, that means whenever the variable point approaches to a from the a minus delta side or taking values which are lesser than a, then to whatever value y or fx approaches is known as the left hand limit and denoted as limit x tending to a minus. This minus indicates that it is approaching from the left side, that is taking values which are lesser than a minus f of x. So we denote it this way. This limit is known as the right hand limit, right hand limit, and this limit is known as the left hand limit. We say that the limit exists. We say that the limit exists when these two limits, the left hand limit and the right hand limit, when these two limits are equal. We say that the limit exists when these two limits are equal. When these two limits are equal, then we say that this limit exists when the left hand limit is same as the right hand limit. So for existence of limit, we can easily check what is the value of the right hand limit, what is the value of the left hand limit. Means again I'm repeating, when x approaches towards say from the right side wherever the functional value approaches, and when x approaches towards say from the left hand side, that is by taking lesser value, wherever the functional value approaches, if the two are same, then we say that the limit exists. That is, if x approaches to the same value when x approaches towards say by all possible paths. Means if you consider the right side, x is approaching by a path. If you consider the left side, x is approaching by another path. Both the paths are linear and part of the same real line, but we can consider them as two different paths. So and actually in this case only two such paths exist. So that's why you are saying whenever if x approaches to the same value when x approaches towards say by all possible paths, here the number of such paths are 2, are same, we say that the limit of fx exists. So we say that limit x tends to a, fx exists, and that is equal to L, that is a value where fx approaches. So this is the basic concept of limit of a function of one real variable. Now let us consider the function. Let us extend the scenario from one real variable to two real variables, from a function of one real variable to a function of two real variables. Let us consider the function z is equals to, let us consider the function z is equal to f of xy, uh, which is a function of two real variables x and y. And geometrically, this will represent a surface, maybe something like this. Let this be my surface, z equals to f of xy. So if I consider this portion of the surface f of xy, then my domain will be something like this. Fine. So this is the scenario if I consider a function of two real variables x and y. So you can understand the geometric shift is from this kind of a curve. Now we have shifted to a surface. Now when we consider this curve in a similar way, my domain had been this. If I consider this portion of the curve, my domain is an interval of the real line, a portion or a segment of the real line. And a part of a line. So my domain is a line, linear. Now, if you consider here your domain is planar. It's a segment of a plane. So from a linear domain, we have now shifted to a planar domain. And the whole thing actually will change due to this particular reason. We will see. Here, the domain is the xy plane, and the elements of the domain are points. So let the variable point, now let the variable point, let us consider the variable point. Let us consider the variable point. Say I have a variable point somewhere. I have a variable point somewhere, say xy. Here I have a variable point. And say here I have my fixed point AB. Say here I have my fixed point AB. Now the variable point xy now will move to a fixed point AB. In earlier case, the elements of the variable element of my domain, which was an element in the real line, which is a point in the real line, was moving to another element in the real line, that is another point in the real line. Now again the same thing will happen here, a variable point. Now here points are lying on a plane, so we need to write them in ordered pair notation. So a point xy, a variable point xy, it may lie anywhere in the domain. It may lie anywhere in the domain. For the sake of discussion, I have shown it somewhere. This is approaching to the fixed point A. Now, the case is that in the earlier case, the variable point x, if you consider the previous case, the variable point x, your variable point, if I place the variable point, say, sorry, if I place the variable point, say, at this position, the variable point x can lie in this side, or the variable point x can lie in this side. So in one of the two sides it will lie. And consequently, the variable point ax can approach towards a from two directions or two paths only. Can you tell me in this case? Can you tell me in this case? In this case, how many through how many paths? In this case, through how many paths xy can approach towards AB? In earlier case, x can approach towards A only in two paths. Now in this case, through how many paths xy can approach towards AB? Remember, now you don't have to restrict your walk on a rope only. Means now the situation is not like walking on a rope as you can see above. Now you can walk on this entire plane. So your walk is not restricted in a linear kind of an area, in a linear kind of path only, because now the entire thing is happening in a plane, not on a line. So you can think about that you are not walking on a rope now. Instead, you are walking on a floor of your room. So the thing is like that. So how many paths, through how many paths xy can approach to AB? Absolutely correct. Absolutely correct. XY can approach towards AB now through an infinite number of paths. You can approach towards AB being on the floor of your room through an infinite number of paths. That means if I try to draw some, your paths can be something like this. Your paths can be something like this. Your paths can be something like this. Your path can be this. Your path can be anything. Through any path, xy can approach to AB. So that means earlier we were talking about left hand limit, right hand limit, and for existence, we said that, okay, fine, if we approach to the same value, irrespective of whatever path we are approaching, whatever path x is approaching, if y approach to the same value, then we said that limit exists. If we keep the same concept here, the concept is same, but the problem is in earlier case we had only two paths, so we very easily checked and calculated what is the left hand limit and what is the right hand limit and checked whether they are equal or not. But the problem here is you now have infinite number of paths, means instead of left hand, right hand, you now have infinite number of hands. So the problem is how to check the existence or how to define the thing in this way. So we need to modify the definition a bit, keeping in this thing in mind, because in earlier case you have seen that this definition mod of x minus a less than delta was clearly understood. It is the linear distance between x and a. When it is a line, then mod of x minus a is a defined kind of thing. We know it is a linear distance, and our paths were also linear, so everything was fitting properly. Now our paths may not be linear. As you can see, I have drawn some of the paths, so that segment mod of x minus a needs to be modified accordingly. So this is the scenario. In earlier case, we had two paths, so we said both these values should be same. Now in this scenario, if we extend the earlier definition of limit, let us see how that can be done, how we can extend that. Fine. Limit. Now I have to write xy tends to AB, f of xy is equal to L, means to each epsilon greater than 0, there exists delta greater than 0 such that mod of fxy minus L less than epsilon for all points for all points xy which are different from AB, for all points xy which are different from AB of the domain which belong to some delta neighborhood n of AB. Okay, let me read out quickly once again. Limit xy tends to AB fxy is equal to L means to each epsilon greater than 0, there exists delta greater than 0 such that mod of fxy minus L less than epsilon for all points xy which are different from AB of the domain which belong to some delta neighborhood n of AB. Now the question is, what do we mean by this thing delta neighborhood? We need to understand what we mean by this thing delta neighborhood. So once we understand this, the definition will be pretty simple. So let us see what we mean by delta neighborhood. If this is my point AB, then delta neighborhood of AB, actually this means this is to be read as delta neighborhood. Then the delta neighborhood of this point AB is a region around AB. In a very rough way, roughly, if I say roughly, this is a region around AB. This is a region around AB. This is a region around AB. This is a region around AB whose area depends on the parameter delta. So by delta neighborhood of a point AB, we mean a region around AB whose area depends on the parameter delta. Some examples of delta neighborhood are, the first one is a square neighborhood. This is our point AB. And we can define a square neighborhood as, say, 0 less than mod of x minus a less than delta. and 0 less than mod of y minus b less than delta. This is how we define a square neighborhood. Means the length of each of the sides are 2 delta. So this is how we define a square neighborhood. The second one is a circular neighborhood. The second one is a circular neighborhood. The second one is a circular neighborhood. We can define a circular neighborhood as 0 less than, if it is centered at AB, then x minus a whole square plus y minus b whole square less than delta square. So this is how we define a circular neighborhood, and you can clearly understand both these neighborhoods, both these regions depends on actually the value of delta. If we make delta very small, if we make delta very small, the neighborhood will also squeeze, and as a result all the points which are lying in this neighborhood will come very closer to the point AB. So that is the thing. That's why I said a neighborhood means a region whose area is depends on the parameter delta. Here if you reduce delta, if you choose a, sorry, I made a mistake here, this should be delta. I don't know why I wrote a b here. This should be delta. So the thing is that if you choose a small delta, your 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 area will be squeezed and all the points will come closer to AB. Or the region can be anything else. I have chosen two very trivial kind of neighborhoods, two very popular kind of neighborhoods, square and circular, and you can choose any other neighborhood, but the thing is that the area you need to choose in such a way that the area depends on the parameter delta, so that you can squeeze the area by choosing smaller value for delta. You can control the area. That is the thing. So this is how we define a neighborhood. So if we consider the definition again, so the definition says whenever the variable point lies in this kind of a neighborhood, in any neighborhood of the point AB, means if we get this kind of a neighborhood, if we get this kind of a neighborhood where this xy xy lies, whenever a variable point lies in this kind of a neighborhood, then fxy if lies closer to L, then we say that limit xy tends to AB is fxy is equal to L. So now let us see what happens to what this geometrically means. So if I consider again this particular diagram, so this was our point AB. So this was our point AB. This was our point AB. Now, if we consider, so let me plot it in one side of this diagram because it is looking too clumsy. Let me plot this xy plane separately. Suppose this is the scenario of the xy plane, and this is my point AB. Let us consider a neighborhood, say a circular neighborhood centering this point AB. Let this be the circular neighborhood centering my point AB. So let us consider now this be my value L. Let this be my value L. Let this be my value L. So the definition says whenever xy, your variable point xy, belong to this neighborhood, which is circular here, you can see in the left side, diagram, whenever a value xy belong to this neighborhood, if the value of fxy come closer to L, then we say that limit xy tend to AB, fxy equal to L. Now, xy can come to this neighborhood by any path. So if I consider, say here my variable point xy lies, if I consider here my variable point xy lies, so xy can xy can approach to AB by any path. Say my approach path can be like this, my approach path can be like this, my approach path can be like this, even my approach path can be something like this. There can be any approach path by which xy can approach to AB. In fact, there will be infinite number of approach paths. Remember, remember, if you make the value, if you make the value of delta, if you make the value of delta smaller and smaller, the neighborhood or this region will also become smaller and smaller, and every point which lies in this neighborhood will become very, very close to AB. Now, since xy can come to this region or this neighborhood by any path, for a small choice of delta, the condition tells that xy xy has come very close to AB, whatever the path may be. Means by whatever path xy is coming to this region, if I squeeze, if I decrease delta, if I make delta smaller and smaller, the region will squeeze. As a result, irrespective of whatever path xy has taken, if I say xy is lying in this neighborhood where this delta is very small, that means the radius is very small. If I say this delta is very small, that means if I say that this delta, that is the radius, is very small, that means whatever path it takes to come to this neighborhood, if delta is very small and if xy falls in that neighborhood, we can say very clearly that xy has come arbitrarily close to AB. So, and if in that situation, if mod of fx minus L less than epsilon, if mod of fxy minus L, sorry, if mod of fxy minus L less than epsilon, that means if I consider this kind of an interval, say this is L plus epsilon, this is L minus epsilon. So whenever by any path, by any approach path, xy is lying in this neighborhood, and if we make delta very, very small, the neighborhood will also become very, very small. So xy and AB will become very, very close. And in that case, and in that kind of a situation, if fxy, that is the value of z, also lies in this interval, and if this epsilon is also very, very small, that means we are saying, that means this definition says that whenever your xy and AB are very, very close, then if xy is very, very close to L, we say that limit xy tends to AB, if fxy is equal to L. That is what we have discussed in the earlier case also. Whenever x is very, very close to a, if fx is very, very close to L, we said that the limit exists. Now a simple extension by bringing the concept of neighborhood, so that we can take all the possible infinite number of paths into consideration. That's why instead of any specific line or path, we have considered a region around the point or a neighborhood around the point, so that all the paths can be considered at the same point of time. So if under that situation, whenever xy is very, very close to AB, if fxy is very, very close to L, we said that the limit exists, and that is what is mathematically written in this definition. Actually, this definition tells only this thing, that whenever xy becomes very, very close, whatever the path may be, if xy becomes very, very close to AB, whatever the path may be, if fxy becomes very, very close to L, we said that the limit exists. So, to summarize this definition tells us that whenever xy approaches closer to AB through any of the infinite number of possible paths, fxy approach or fxy approaches closer to the value L, then we say that limit xy tends to AB, fxy equal to L. So if I just write one line, what this definition tells us? This definition tells us that fxy should approach. This definition tells us that fxy should approach to the same value fxy should approach to the same value for all approach paths for all approach paths of xy to AB. So fxy will approach to the same value for all approach paths of fxy to AB. Now for all means for all infinite number of approach paths. We need to keep in mind the number of approach paths are infinite. Now keep in mind that two things are very important. Fx should approach to the same value, and this for all. These quantifiers are very important. Fx should approach to the same value for all infinite approach paths of xy to AB. Now, why the number of approach paths are infinite now? I am again reminding you, because now the domain is a planar, and the situation is you are walking on the floor of your room instead the earlier situation where you were walking on a rope. So that is what is meant in this definition. Now let us apply this definition in solving a problem. Let us see how we can solve problems using this definition. Let us apply this definition in proving that limit xy tends to 0 0, limit xy tends to 0 0, xy into x square minus y square divided by x square plus y square equals to 0. Later we have to solve this problem. The question is prove that limit xy tends to 0 0, xy into x square minus y square by x square plus y square equal to 0. Let us suppose we have to solve this problem. Let us simplify the expression a bit. Let us simplify first the expression a bit by substituting. Say, let us simplify by substituting, say, x equal to r cos theta and y is equals to r sine theta. Let us simplify a bit. This came to my mind seeing the denominator x square plus y square. So if you plug in this, then we get mod of xy into x square minus y square divided by x square plus y square. Mod of this is equal to, we can write this as mod of xy means r square cos theta sine theta. So r square cos theta sine theta, that means I can write that as r square by 2 sine 2 theta, and here I will get x square minus y square. So r square into cos square theta minus sine square theta, that means cos 2 theta, and r square will get cancelled. So it is r square by 2 cos 2 theta. You simply substitute, you will get to know. Why? Because we know that sine 2 theta is equals to 2 sine theta cos theta, and cos 2 theta can be written as cos square theta minus sine square theta. Am I right or not? Okay. So in a similar way, this can further be written as mod of r square by 4. Now 2 sine 2 theta cos 2 theta, if I do this adjustment, so it will be sine 4 theta. So that means this will be equals to mod of r square by 4 into mod of sine 4 theta. That means this can further be written as less than or equal to mod of r square by 4. Mod of r square by 4 actually is same as writing r square by 4. So this is same as writing r square by 4. Why? Because we know that sine phi, the mod of sine phi will always be less or equal to 1, whatever be your phi. So that means we got that this expression is less or equals to r square by 4. Therefore, we can say, therefore, mod of xy into x square minus y square divided by x square plus y square less than or equal to, now r square means r square is what? R square is x square plus y square. So this is less than or equal to, I can write x square plus y square divided by 4. x square plus y square divided by 4. And this will be less than epsilon if this x square by 4 is less than epsilon by 2 and this y square by 4 is also less than epsilon by 2. That is x square by 4 less than epsilon by 2. That means I can write, if I simplify, 2 epsilon, x square less than 2 epsilon. So if that means if mod x, that is mod x less than what? Root 2 epsilon and mod y less than same root 2 epsilon. Now, can you tell me what we have to show actually? If we have to prove that the value of this limit is equals to 0, means if we have to prove this, what do you have to show? Let us go back to the definition once again. The definition says that to each epsilon there exists a delta. That means we know we have to show that whatever epsilon I choose, there will be a delta and there will be a delta neighborhood. Whatever epsilon I choose, there will be a delta and there will be a corresponding neighborhood such that whenever xy belong to that particular neighborhood, mod of fxy minus L is less than epsilon. So basically, we need to show that whatever be the epsilon, there exists a delta neighborhood. That is, we need to show. That means we need to say what is my neighborhood or what is the region, and more specifically, what is delta for a given epsilon. That means the relationship between epsilon and delta. That is what we need to show. Fine. By exploring the condition, the thing that was given to the function, what we get? We got this. That means now we need to say what is my delta? What is my delta? And what is the delta neighborhood? Fine. If we choose delta, let delta I am choosing as equals to root 2 epsilon. If I choose this as my delta, then let us see what we can write. If we choose in this way, then we can write firstly this part. This part can be written as mod of xy into x square minus y square divided by x square plus y square. So you can very easily understand this can be written as minus 0. So if I write this minus 0 less than epsilon, if these two conditions are true, that means I can write less than epsilon whenever what? Mod x less than root 2 epsilon. Now, as per our this supposition, root 2 epsilon is delta. So I can write mod x less than delta. Now, mod x is same as mod of x minus 0. And the other one gives me similarly mod of y minus 0 less than delta. Now, what is this mod of x minus 0 less than delta, mod of y minus 0 delta? What this represents? If I look at the earlier examples, this mod of x minus, here a is 0, mod of x minus 0 less than delta, mod of y minus 0 less than delta. So what this represent? This represent a square neighborhood. That means this expression, this inequalities represents a delta neighborhood of which point? Of the point 0, 0. Now here my AB is 0, 0 for this particular problem, and this inequality further represent that xy belong to n delta 0, 0. If we represent this square neighborhood by the symbol n suffix delta 0, 0. N means neighborhood, delta is the delta is the parameter on which the area of this neighborhood depends. That's why I've written delta. Here it is a square of where each of the sides will be 2 delta and the center 0, 0. Sorry, around 0, 0. So n delta 0, 0. That means what we got? we got that this is my fxy for the question. This is my L. So we got mod of fxy minus L less than epsilon whenever xy belong to n delta 0, 0. So I have clearly shown you what is the neighborhood. If you give me any epsilon by virtue of this relationship, I can tell you what will be the corresponding delta. If you give me any small epsilon, smaller than the smallest that you can think, that means if you make this function fxy and L very, very close, by choosing an epsilon, maybe that is smaller than the smallest that you can think, I will tell you by this relationship what will be the corresponding delta where xy, your variable point, and 0, 0 will lie, and how much close they will come. So I can tell you that. So that means this calculation tells us that whenever xy becomes very, very close to 0, 0, your function, this fxy, becomes very, very close to 0. That means we can now say by virtue of the definition that limit xy tend to 0, 0, xy into x square minus y square divided by x square plus y square equals to 0. That is how we have proved it from the definition. So we have categorically validated the definition. Whatever is the definition written here, we have categorically validated that. Now see, why we have done all this? Because in case of functions of one real variable, you have never applied the definition to validate the existence of limit. Instead, you have checked the right hand limit and the left hand limit. But the problem here is we don't have only right hand and left hand now, as I have told repeated number of times in this video. We have now infinite number of approach paths, means infinite hands, and checking the equality for all those infinite paths is not possible. That's why we have no option but to rely on the definition, and this is how we can use definition to prove the existence of limit. And the point is, what we have to do, we have to find out a relationship between delta and epsilon, and we have to specify what is the neighborhood that I'm talking about. These two things we need to find out, so that to every epsilon I can say clearly what is the delta. So if we look at this, if we look at, say, this statement once again, if I look at this statement once again, actually this statements tell us lots of things. If we look at this particular statement once again, then what it says that fxy should approach to the same value for all infinite number of approach paths. So that means if I get any two paths through which xy approaches to AB and fxy are tending to two different values, what that will mean? This says that whenever fxy approach to the same value for all possible approach paths, if fxy approach to the same value for all possible approach paths, in that case only we can say that the limit exists. So as a counter example, if I show you two approach paths via which when xy approach to AB, we get different approach points of fxy, what that will indicate? That is absolutely correct. That will indicate that the limit does not exist. So this tells us a way of how to prove non-existence. To prove existence of limit, we have no other option but to rely on the definition. But to prove non-existence, we have a way out by giving a counter example. Pick up two paths which lead to different approach points for fxy, and that will tell you that the limit does not exist. Let us see this through an example. Let us consider, let fxy, let us consider another example. Let us consider, let fxy is equals to x square y divided by x to the power 4 plus y square. That is, if the denominator, that is x to the power 4 plus y square, is not equals to 0. And this will be 0 if my x equals to y equals to 0. So let this be the scenario. This is my problem. Let us see. Let us see what happens. Let us see what happens when if I try to find out. Let us see what happens with the limit xy tends to 0 0. This fxy. Sorry, xy tends to 0 0. F of xy. Try to find out. Let us try to find out what happens with this. Whether it exists. If exists, then how, or it does not exist. See, if we that means here the variable point xy approaches to the origin. The variable point xy approaches to the origin. The variable point xy approaches to the origin. So let us have the xy plane. Okay, so this. Now see, there can be if xy is any point in this two-dimensional plane, then it can approach to this origin through any path, as we have said. For example, if xy approach to the origin, say along this axis, along this two, any of the two axes. For example, if it approach to this along this line. This line means the equation of this line is y equals to 0. Or similarly, if xy approaches to the origin via this line. This line means our x is equals to 0. X is equals to 0. So again, when x is equals to 0, the functional value is 0. So we can say if the approach path is if the approach path is the axis, so we can write if xy tends to 0 0 along axis, along any of the axis, fxy tends to 0. So if these are my approach paths, maybe this line or this line. So if I pick up this line as an approach path and this line, if I pick up these two lines, then fxy tends to 0. Does that mean that the limit xy tend to 0 0 fxy will be 0? No, because there can be several other paths. For example, now let us consider that the approach path is not like this, but the approach path is any straight line through any straight line passing through the origin. Let my approach path is any straight line passing through the origin. Let this be my approach path. Say this is y equal to mx. Any straight line, maybe for some value of m, let this is y equal to mx. So then if this is my approach path, then let us see what happens. Then if we simplify the expression, then f of xy means y is mx. So f of x mx will be x squared into mx divided by x to the power 4 plus m square x square. So that means m square x square. So that means this will be equal to mx divided by x square plus m square, if we cancel out the x square. So that means this will clearly tend to 0. This will clearly tend to 0 as this will clearly tend to 0 as x tends to 0. Now, why this line is chosen? Because this is a line. See, remember, your limiting condition is xy tend to 0 0. Xy tend to 0 0 means you have to choose that path where x tends to 0 will imply y tends to 0, because xy is tending to 0 0 means simultaneously x and y both are approaching to 0. So as a point they are moving to 0 0. Now, if you consider this particular path, so this xy tend to 0, 0, if I replace this y by mx, that is equivalent to saying x tends to 0, because when x tends to 0, automatically y tends to 0. So if I consider this substitution, if I replace y in terms of x, that means xy tend to 0, 0 means x tends to 0. And we can see here, whatever be your straight line passing through the origin, straight line may be this, maybe this, straight line may be this, straight line may be this, whatever be your straight line passing through the origin, whatever be your straight line passing through the origin, it doesn't matter, whatever be your straight line passing through the origin, always the function, if xy approach to the origin along that particular path, maybe along this path or 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 this path, whatever be your path, along this kind of, remember these are all lines, my drawing skill is pretty poor, these are all y equal to mx for different values of m. So whatever be your line, if the point approaches to the origin along all these paths, then the function will tend to 0, as this shows. Now, will this imply that limit xy tend to 0, 0 fxy is equal to 0? Because there can be infinite number of straight lines passing through the origin, and whenever xy approaches to 0, 0 along any of those infinite number of straight lines, the function tends to 0. So will this imply that the limit is 0? Absolutely not, because there can be so many other type of paths than these linear paths. These are quite only some of the examples. For example, if I consider, say, if I consider a path which may be looking like this, maybe this, or which may be looking like this, or my path can be looking like this, like this. That means actually, which kind of path I am saying now? I'm thinking about now paths which are actually, which can be represented or which can be defined as y equal to, say, mx square for some value of m. Instead of y equal to mx, now I'm considering paths which are y equal to mx square. Let us see what happens. So here also you can see x approaches to 0 implies, if x tends to 0, y will tend to 0. That means along this path also you can reach to the origin. So x tends to 0 implies y tend to 0. So if I substitute y by mx square, then xy tends to 0, 0 can be treated as x tends to 0 only. So if I do this substitution, I get f of x comma mx square will be equal to simply I can write here, will be equal to, what will be x, if I replace this will be my function will become m by, because the x to the power 4 will get cancelled from both the sides, so it will be m by 1 plus m square. Now there is no x present here, so so we can say this tends to m by 1 plus m square as x tends to 0. Now the problem is, if you change values of m, so in this particular curve, suppose in this particular curve m has some value a, and in this particular curve suppose m has some value, say b, because the two are different curves, two will be obtained for different values of m. So if these two, for these two, if m is equal to a and m is equal to b, then if you plug in the value of m here, you can see when x approaches to 0 or xy approach to 0, 0 via these two paths, your function approach to completely two different values, a by 1 plus a square and b by 1 plus b square. So for different values of m or for different choice of paths, we will get different approach points of fxy. That means by definition we can say the limit does not exist. For example, if I choose, say, if I choose a path y equal to, so I can say along, along y equal to x square, fxy tends to half, but along y equal to say 2x square, fxy approaches to fxy approaches to 2 by 1 plus 4, 2 by 5. So you can see clearly here fxy approaches to half, here fxy approaches to 2 by 5. So fxy are going to two completely different approach points. That means by definition we can say that this limit does not exist. So this is how, by showing counter examples, we can prove that the limit does not exist. And remember, if you get like the previous case along the axis lines or along y equal to mx, we have seen that we were getting the same approach points. But remember, if you get for some curve, for a finite number of curves, or maybe for a family of infinite number of curves, if you see that fxy approach to the same value, that does not guarantee that the limit will exist, because there may be some other type of curves, maybe some other family of curves which might produce a contradiction. So to prove non-existence, our task will be to find out that family of infinite number of curves, and that family of infinite number of curves where you get different approach points for the function when the variable point moves to the limiting point. If we get different approach points, we need to so that we can say that the limit does not exist, and we need to search for those kind of a family, as we have got here y equal to mx square, because you have seen at the end everything cancels out and the limit becomes the function becomes a function of the parameter m. So if you change the parameter, you will change the curve, your paths will change, and accordingly the value of the approach point will also change. So that will prove the non-existence. So to prove non-existence, you need to provide counter example. But remember that how this is done. Two basic things you need to keep in your mind, that the approach point needs to be maintained. For example, here I cannot choose a curve like y equal to mx square plus 2, because y equal to mx square plus 2 will not satisfy the approach of limiting point. Y equal to mx square plus 2, if I write, then y tends to 0 implies, sorry, then x tends to 0 implies y tends to 2. But my condition is xy should tend to 0, 0. So my choice cannot be y equal to mx square 2 or mx square plus 2 or mx square plus 3. My choice has to be y equal to mx square if I have to meet this criteria. So while choosing a family of curves or a family of paths, you need to keep that in your mind. And the second, you need to inspect the function very carefully so that after substitution, everything gets cancelled out and you can get the function only a function of the parameter. That is how. Now there is no rule to find out this substitution. It is basically by observation. You need to observe the function very carefully, keeping in mind the two issues which I have told. The limiting point criteria should be matched, and number two, everything should get, all the variables should get cancelled out, only you should get the function of the parameters. So this is how we prove non-existence by showing counter example, and this is how we prove existence from the definition. So that's it for this video. This video became quite lengthy because we discussed so many things which are highly conceptual. I'll end this video by giving two problems to you, two problems for you to solve. The first one is show that, homework. Two problems for you to solve. The first one is show that limit xy tends to 0, 0, square root of x square plus, sorry, square root of x square into y square plus 1 minus 1 divided by x square plus y square equals to 0. So you have to prove that this limit is equals to 0. And the second one, show that limit xy tend to 0, 0, x cube plus y cube divided by x minus y does not exist, so that this does not exist. So I'm leaving these two problems for you to solve. uh, for the first one, you understood very easily that the first one needs to be proved from the definition, and for the second one you need to search for a counter example. So try to solve the problems and let me know in the comment section below. That's it for this video. Take care.